Well, my name again, I'm going to repeat very fast. My name is Jaume, and together with my colleagues, José Luis Leiva, Rosa Mateos, and Roland Duhart, we have been preparing these slides. This is the index when we're talking about the introduction of virtual antenna. How easy is to design IoT devices embedding virtual antenna with encrypted models that are available for CST Studio Suite. And we are going to use some examples to show how easy is that. We are going to see some LoRaWAN devices, which is a single band. We are going to do a more challenge case, which is for multi-band LTE. Then we will move to a tracking device combining GNS and Bluetooth. And finally, with example 4 and 5, we are going to see cellular tracking devices with combination of LTE and GPS, as well as GPRS and GNS. Okay, as you everybody know, we are living in the IoT world, in the IoT era. So not only people and people will be connected, but also people with things, things with things. So this at the end means that everything will be connected, and the challenge is that we need very sophisticated devices that are efficient, they transmit all information in real time. So to do that, at the end we need a very small and multiple antennas. So this is the challenge that we have for the community in these times. And here is where virtual antenna takes place. Virtual antenna is a technology that embeds tiny elements called antenna boosters. You can see in this picture, these antenna boosters in IoT devices. So you can operate for any band and for any device. For instance, imagine you have a device like this, like a IoT device, big in size or small in size, or for instance like this, like a smartwatch. No matter the form factor of the device, you don't need to use a different antenna. You don't need to customize a complex geometry for the antenna. You can use the same tiny antenna booster, which is pretty small, and the only thing we need to do is to design a matching network, which is very fast and systematic, as we can see with CST. Now, we can also operate for any band. Imagine we have this device here, and for one device, we need to operate at ESM bands. But now we have to launch a new IoT device with the same platform, but now we want to operate at some bands of LTE. The question is, do we need to change the antenna geometry? Do we need to change the antenna product? The answer is no. We can reuse the same antenna booster, and by only changing the matching network, which is really fast, we can now operate at any band we want. So at the end, the difference between the virtual antenna approach and the geometrical based approach is that the bands are not fixed by the geometry. The bands are fixed by the matching network that we add to the antenna. So it's like designing any other chip, like an amplifier or filter. You get the component, you just put the matching network, and that works. In a similar way, this can be like this approach for antenna design. No more using a complex geometry, but using a very simple structure, and by adding a simple matching network that we can do in a systematic way, we can operate for any band and for any device. So besides being a small component, the antenna booster is pretty small. For instance, in this case, you have a cube. It's only 5 by 5 millimeters. So in terms of lambda, it's lambda 30 if we operate at 900 megas, for instance. So besides being small, they are multi-band or multi-communication system. They have also nice features. For instance, these components, these antenna boosters, are off the shelf. You don't need to customize the antenna booster. It's already done. So you can start your IoT device and the antenna is already done. You can use as the same way you use an amplifier or a chip. You don't need to design from scratch. And this is very convenient if you want to go fast in the designs of IoT or any wireless device. Another attractive feature is that the component is pick and place. You can see here we have some pads for the component. So this means that this antenna booster can be assembled in a PCB following a standard process which is called pick and place. It's like a robot that takes the antenna and directly mounts this PCB, this antenna booster on the PCB. So this avoids human error. So at the end, we have that the antenna booster of virtual antenna, it's small, it's multi-band or multi-communication, it's off the shelf, and it's pick and place. So this makes a nice future and very attractive for the IoT ecosystem. What is the markets that with virtual antenna we can address? All the wireless devices, IoT devices, in operating in this frequency range of 0.5 gigas up to 10.4 gigas. It means everything with LTE, GPS, they do GLONASS, ISM, LoRaWAN, and whatever is included in this frequency range can be addressed very easy with virtual antennas. So the markets at the end is tracker devices, smart meters, smart home and city applications, modules, and sensors. So everything for the IoT world and related applications. And here we have a general picture of the evolution from first external antennas, that were usually monoband and quarter wavelength monopoles. Then they appeared the first internal antennas for mobile phones back in 1996, 1991, 1999. And then the volume shrinks down, and about the volume, the typical volume is about 1,000 to 1,000 millimeter cubes. So just to give a glance view of how small its virtual antenna, the antenna boosters of virtual antenna, it's about one order of magnitude less. With only 100 millimeter cubes, we can handle all the bands of LTE, GPS, and so on for IoT devices. And you can see here that the nature, from the technical point of view, the nature of these antennas is non-resonant. So at the end, what we do is we add a matching network to operate at any band, and this process is very, very easy and fast. Let me share with you a video that summarizes the antenna very fast. I'm going to share this video with you.
In this super duper smart modern world, connected things are everywhere. Whether you're managing a fleet of trucks, running a smart city, or just checking your fridge, you'll be using antennas to plug into the mystical wireless IoT world.
Last night, you ate 3 pizzas. Shall I order more?
Shh, fridge! Don't be so smart. Anyway, for you guys trying to figure out which antenna is right for you, the whole process can drag and suck up all your patience and money until you find yourself screaming, "Please help me!" But now, your antenna nightmares are over. Introducing the one, the only virtual antenna. This little genius is multiband. It works to any standard or frequency. NB-IoT, LoRa, Sigfox, Wi-Fi, GPS, 3G, 4G, 5G, or whatever G they come up with next, probably 6. And because it's tiny and delightfully versatile, it'll fit in any wireless product, regardless of the form factor and frequency band. Your friendly new little antenna component works just like another chip. Need to reduce your time to market? Use virtual antenna on your project so you can move fast. On to the next one. Or sit back, relax, and
eat more pizza.
Fridge. Oh, go on then.
Okay. Let's share again my screen. So these are some real examples of the virtual antenna integrated in IoT devices. The first one is open platform for IoT, cellular GPS, GNS, with NG91 binary semiconductor, strength of sensor, humidity, speed, position, air quality, as well as this nice open platform too by Mango Yellow Sierra Wireless. And you can see both. The component here is the antenna booster, one type, and in here we have another antenna booster in a very small platform. This is a platform of only 50 by 50 millimeter, and this is like a credit card. So this is a really challenge in the wireless design. When you have a small platform, it's really a challenge to design small antennas. Okay, so let's see which is the design flow chart for virtual antenna. It's quite easy. And just step one is to select the antenna booster, the best antenna booster that fits in your device, and place in the best position. The second step is, once you have the antenna booster in your device, is to design the matching network. And the third step, you all know, is to measure the device in terms of S1, S parameter, as well as efficiency and radiation power. So let's see these very nice videos just to summarize all these 3 steps. Let me check, and I will share the videos.
Step 1. Placing the antenna component. This is the fantastic device you're working on, and let's say it's a mobile device. The simpler, the better. First of all, pick one outer corner on the PCB. Better take the longest side. Perfect. Okay, let me guess. Your device is different in terms of shape. No problem. Here are some examples. Where would you place it in an IoT device? Yes. Cool. This tiny antenna component will need a clearance area in the ground plane layer. And also a keep-out space free of any metallic elements in all directions. Less than 5 millimeters could be too close. That's it. Now that you know the spot, let's mount it to the PCB. You'll only need a set of pads and a strip line from the antenna to the RF system. And ta-da! Easy, right? You're ready for step 2.
Before moving to step 2, you saw that usually, as a rule of thumb, putting the antenna in the corners is the best position. We have more papers, more information that we will share with you at the end on how to handle this, but the rule is easy, to put the antenna at the corners of the PCB. Let's share the second video.
Step 2. Designing your matching network. Many antennas need a matching network. Why? Simple. Without it, your antenna would reflect some radio waves back. Here, we'll learn how to design a matching network to optimize the transfer of energy to the antenna component. But what exactly is a matching network? It's a specific combination of inductors and capacitors to obtain 50 ohms of antenna impedance. In only 3 steps, you can design a basic matching network. First, place a series inductor in the PCB to compensate for the booster's capacitive impedance. Then, a shunt inductor to match. You might need a series component to fine-tune the frequency response. If you were working on a device running within 800 to 900 megahertz, these would be the approximate component values. Now your antenna is working. Congratulations! Ready for the test?
Well, in this example, we see just a matching network that is useful for single band, but now we are going to see more examples on how we can handle the design of the matching network. Let me share with you the final video, step number 3.
Step 3. Testing your device. This is the moment of truth. Let's figure out how your antenna is running. The easiest way to start is a field test. Close your device with all the covers and protections, switch it on, and be proud of your work. Fine-tune the matching network if needed. But maybe you want to be more accurate. To really test the impedance, you'll need to use a network analyzer. To do so, place a 50 ohm microcoaxial cable and ground it at 3 or 4 points. Check the matching value within your frequency range and adjust the matching network to reduce mismatch. Now your device is prepared for the final test, the anechoic chamber. This first-class room will be your perfect ally to test the antenna's efficiency. Bravo! Your device has a brand new antenna in the smallest space you've ever possibly imagined.
Okay, so let's go back to the presentation. So this single step summarizes the flowchart from placing and choosing the antenna booster, then designing the matching network, and testing your device. Just to be on the same page, I'm going to share only this equation that this is total efficiency we are going to use. The total efficiency at the end takes into account the ratio between the power radiated into space over the available power. And this takes into account mismatching with the 1 minus S11 squared 2, and all losses of the system, not only the plastic covers, the battery effects and whatever, but also the matching network losses, if any, into account. So this at the end is the number that we are going to use to assess our performance. And for instance, this is very practical for particularly in some IoT devices if we need to fulfill some TRP certifications, total rated power. For instance, imagine your module is connected here and it's represented by this circuit. If the module transmits a power of 23 dBm, if we know that the total efficiency is, for instance, 50%, at the end, the total rated power into space will be this 20 dBm. So this number that can be simulated, as we are going to see with CST, and compared with the measurements, it's a really good number to compare and, well, to assess that the device is working properly. Okay, here we have all the products from virtual antenna. We have several products with different shapes because, well, every device is unique. So sometimes you have less ground clearance, you need more bands, you need to operate several communication systems. So here we have several products, and all these products are now encrypted, so they can be used by anyone who has the CST in their IoT device. We will explain at the end of the presentation how you can download these encrypted models and how you can use it for your IoT designs. So let's see now some examples just to understand how not only the technology works, but also how these encrypted models are easy to use in the design of IoT devices. The first example will be with this antenna booster, which is called the run and extend. It's really a small antenna element, 12 millimeter by 3 by 2.4. And you can see that this is lambda over 30 at the frequency of 824. So it's really, really electrically small antenna. So this antenna booster, we are going to see two examples. The first one will be a very easy one, single band, and then we will increase the complexity of the design by using a multi-band design. We are going to operate at several bands of LTE, from 824 till 960, 1.7 gigas up to 2.69 gigas. So here is the product, as you can see, and the encrypted model has all the materials, all the geometry, even the color, the part number, everything is the same. So you can use, as you use any chip, like amplifier and so on, you can just take it and you can now use it in your CST designs. Let's see an example of how we can use this encrypted model. Imagine you have your PCB. This is a particular easy example with non-populated. At the end, we are going to see populated PCB, but just to start with a single example. This is your PCB. In green color will be the ground plane. In green will be the electric of your PCB. Typically it's FR4 for most of wireless devices. In here you can see, well, this is the path layout for your matching network. It can be reduced if you have less number of components. In this case, we put more space to allocate more components. Here is the encrypted model, the antenna booster, with the pads in this orange color on the left and the right. They are the connecting pads. And well, now it's easy to import this to the model, and by some translation and rotation, just you can place this antenna booster on your PCB, and that's all. So this step one is done. We choose the antenna booster and we place the antenna booster usually at the corner of the device. And that's all. We are ready to simulate this structure so we can obtain the S parameter, and with those S parameters, we are going to design the matching network. So we are going to do the step number 2. The step number 2 is to design the matching network. As we see in this slide on the left, we see that the antenna booster with no matching network is reactive. It's a non-resonant element. So the antenna does not operate here unless you put a matching network. You can see that it's quite reactive. So in terms of S11 in dB, it's very poor match. It's about minus 1 dB. So all the power reaching the antenna booster will reflect back. But well, that's not a problem because we can easily design a matching network and put this impedance at the center of the Smith chart. In this case, we use a very simple matching network. We can do it with 2 or 3 components for a single band case, like this is on LoRaWAN, And you can see that now the S11 is very close to the center, and now we have an S11 less than minus 12 dBs across the LoRaWAN frequency bands of operation. So it's easy. The antenna now is ready, and you can take these components built in your PCB, and the process is finished, ready for step 3, that will be to test this in an anechoic chamber with a vector network analyzer, and that the process finishes. And also, please see the advantage of this. Imagine that you want this device, but now you don't want to operate a LoRaWAN around 800, 900. You want to operate at GPS. Well, the only thing you need to do is to change the matching network. Or you want to operate at around 700 and so on. You change the matching network. So to operate at any band, the only thing to do is to change the matching network. And this is very fast. However, designing a new antenna from scratch, it's time consuming. This is a single band case, which is very, very simple and straightforward to match the antenna from this area to the center by engineering rules. We don't need sophisticated equations. But here, let's see another example. We are using the same platform, the same ground plane we saw before. Okay, the antenna booster, this one here, it's only 12 millimeter length. It's about 130 and 100 megas. And in this case, we are not going to match around LoRaWAN, around 800, 900. We are going to operate at 4G. We are going to operate from 824 up to 960 megas, and from 1.71 gigas up to 2.69 gigas. Here, well, the bandwidth is more challenged. You have more bandwidth, and also it's multiband. So, well, the thing is that with CST, we can take into account the path layout for allocating paths. So all the parasitic effects, all the delay introduced by the paths are taken into account in the simulation with CST. In this case, the port number 1, 3, 5, and 6 are useful to allocate various SMD components like SMD 0402, and port number 2 and port number 4 are useful to allocate shunt components like L and C in shunt. And the port number 7 is the feeding port, is the 50 ohm feeding port where we are going to connect our front-end module. So the design of this matching network that maybe can have up to 7 components, we can address from our experience. We have experience in designing matching network, but if not, no problem at all. We can do it systematically and in an automatic way by using Opteni Lab that has a link with CST. So once we get the simulation, the S parameter from CST, we export this matrix. This is an S matrix 7 by 7 because we have 7 ports. This is in green color. And we say to Opteni, okay, I want here one component, another here, another here, another here. I don't know if it's an L or a C, and I don't know the value. Let the Opteni work for us. And also, please don't use ideal components. Use commercial values. For instance, please choose Murata components of the series SMD 0402, or you can combine several libraries. And the port 7, it's a short circuit because here we have just our feeding port. And after 2 or 3 minutes, you get the matching network. So you get all the components, if it's a L or a C, and once you get those components, we are done. The design of the matching network is finished. It's only on 2 or 3 minutes, which is really fast. So here is the simulation with CST. We obtain the S parameters. We import to Opteni. If we have to design this matching network, which is multiband, we obtain this matching network with 7 components with these commercial available values. In this case, from Murata, but there are many, many other vendors. And the same values that we obtain in the simulation, we put in the real PCB, the very same, without any change. And we go to the lab and we do step number 3. So we test our device, and the results are here. In green, we have the simulation with CST taking into account all the losses on the PCB, in the FR4, in the matching components. So everything is taken into account with CST. And we build this PCB and we compare the antenna efficiency that takes into account mismatching and losses. So this is measured in an anechoic chamber, in a 3D anechoic chamber by Satimo. And you can see the very good agreement between the measurements and the real and the simulation and the measurements in the low frequency bands as well as the high frequency bands. The difference between simulation by CST and measurements, it's around 0.02 dB and 0.3 dB in average. So it's pretty nice, and without any human intervention, just the matching network we obtain, we go to the lab, we build it, and stop. It works. Obviously, if you have more RF skills, you can do some fine-tune in case you need to improve some matching. But if not, the process is finished. So it's very fast and very systematic to design either single band or multi-band antennas with virtual antenna using this antenna booster and this process with CST and virtual antenna technology. Well, just a comment on radiation patterns. Naturally, also CST can handle with radiation patterns, gain, and so on. In here, you can see that for these devices, the radiation patterns are usually omnidirectional with low directivities about 2, 3, 4 dBis, which is good for wireless communication. It's ideal because you don't know where is the base station. So at the end, what you would like to have is some kind of isotropic radiation pattern in your IoT device. Let's move now to another example. In this case, what we have is another component of the family of virtual antenna. It's called Duo, and it's called Duo because this is a dual port antenna, and we explain in our user manuals how we can use this, and also for the user manual for CST, how you can fit this antenna in one port to operate at global navigate satellite systems, such as GPS, GLONASS, Beidou, whatever, in this frequency range, as well as in Bluetooth. Also, the advantage of these components is that, well, you can operate in even Wi-Fi dual band because at the end it's to design a new matching network. But in this case, we're going to see one example in operating at GNS and Bluetooth. Again, you see the antenna booster is very small. It's lambda over 30 at the GPS, at the GNS frequency bands. The component is 7 mm by 3 and 2. And this is the real component. And this is the encrypted model with everything, the real mechanics, the geometry, the materials from the vendor, it's included and take it into account in the encrypted model by CST. Let's see this video where we see the PCB. Again, it's a bare PCB with all ports. In this case, the antenna is not mounted at the corner. This is a particular antenna booster that can be mounted in the middle of the PCB. So it's convenient in some circumstances that perhaps you have all the corners occupied by other antenna boosters for operating at LTE bands or MIMO and so on. So you don't have to pay for GPS and Bluetooth. Well, you can use the middle edge and you can allocate this component to operate GNS and Bluetooth. Here you can see the details of the antenna booster, the Duo antenna booster. And again, by applying some rotations and translations, we put this component in the middle of the PCB. As you can see, on the left, we have the pads for the GNS matching network. And on the right, we have the pads for the Bluetooth matching network. Well, and this is an example. You can also model coplanar waveguides put in the center, microstrip lines, any kind of transmission line can be modeled. In this case, it's an example, but other kind of transmission lines for feeding the antenna booster can be also handled by CST. So we are ready. The antenna booster has been mounted. This is step number 1. And step number 2 is to design the matching network. So once we have the simulation with CST, we obtain the S parameters and we go to the second step, which is to design the matching network. In here we have the simulation in green, and here we have the evaluation board in red with one port with a 50 ohm transmission line, coaxial transmission line to feed the GNS port, and another SMA connector and the feeding 50 ohm transmission line for the Bluetooth and the matching network for Bluetooth. As you can see here, this component has no clearance area beyond the antenna footprint. So it's really a tiny component and also does not occupy any more space, so you can have them put more electronics near the antenna component. And here is the layout. We have the pads for the matching. In this case, port number 5 is for the feeding port for GNS. The port number 12 is the feeding port for Bluetooth, and the other are ports for series component, shunt, series, shunt, series, and shunt. In this case, series, shunt, series, and shunt. In this case, we have more paths just to have more freedom to design, but at the end, you can see that for the GPS branch, we need 1, 2, 3, 4. We need a filter just to improve isolation, and then the matching in here. And for Bluetooth, we only need 2 components. So it's really, really a very simple matching network, a very simple structure that with only 6 components, we can have GNS and Bluetooth within a very, very small antenna component. And now we are done. We have designed the matching network and see the results in terms of S11 and isolation. In green, we have the simulation, and in this pink color, we have the measurements. We see that in the frequency bands of operation, GNS, and as well as Bluetooth, we have S11 below -8 dBs that matches perfect the simulation with the measurement. Again, without any human intervention. The same matching network that we obtain with this systematic approach is mounted on the PCB. We measure and we get the results. You see that the S11 and S22 are pretty much the same. And again, the isolation, sorry, in this case will be the S21. The coupling is very weak, and you see the good agreement. The good agreement, in particular here, it's almost the same. So it's pretty nice how the simulation results agree with measurements. And also the total efficiency. Is again the matching and all the losses. In this case, we have also modeled the transmission lines, because in some cases the front end module is not close to the antenna booster. In some devices, there is some distance between the antenna booster and the front end module. So in those cases, we can use transmission lines like these microcoaxial cables, and these microcoaxial cables can also be taken into account in the simulation process. So you can see here in green, this is the simulation, and in orange, we can see the efficiency across the GNS band as well as in the Bluetooth band. And again, the difference between simulation and measurements is pretty good. We only have about 0.5 dB, 0.4 dB. So it's pretty very well agreement between both. So now we move to the last example. This is called the Trio MX10. It's another antenna booster, and it's called Trio because it's possible with this antenna booster to operate at 3 different communication systems. So for instance, we can operate with one port at LTE, with another port at GPS, and with another port at Bluetooth. In this case, we are going to see another examples. Example 4 will be for a cellular tracking device to operate at LTE and GPS with a very sophisticated matching network. It's a tunable matching network. And example number 5 is another cellular tracking IoT device for operating at GPRS and GNS. And again, this is the real product, and this is the include model. So everything, again, all the materials, the geometry, even the colors, everything is taken into account in this include model. That is a very nice feature that CST has in order to exchange between all the companies and research to exchange our materials without compromising our peers. So we can exchange all materials and everybody can work and exchange materials so we can go faster in the design of IoT. Here is a very nice real example with CST, and this is a nice project that we developed with our colleagues of Nordic Semiconductor. This is the device called Thingy91. It's an open platform for IoT. It has many sensors, humidity, speed, position, air quality, and so on. It's in a very small package of only 50 by 50 millimeter. As you can see here, we have a fully populated PCB. All the mechanics from the customer of the device are given, the SMD, the front-end module, buttons, battery, even the plastic covers. So all the materials, the electrical properties of materials are also taken into account and are easily imported to CST. And the good thing is that CST easily can handle with this robust hexaedral makes all the fine details of the model. So at the end, this can be easily handled with CST, and we can model this complex platform, no matter if it's plenty of components. And here you can see also, again, the trio MX10 with the feeding line at the corner of the PCB, which usually, as a rule of thumb, is the best position to obtain the best bandwidth and efficiency. And here is the real product that was launched by Nordic Semiconductor back in August 2019, and it's already there worldwide, working in many IoT devices. So this is useful because CST is not only useful for generating designs from scratch at the conception phase, if you are designing IoT devices from scratch, but also if you are designing IoT devices and you want to go to production, because we can handle many things. So we can optimize at the very beginning the antenna location, because it's very important at the very beginning of a project to handle the antenna location. If not, it's difficult to handle in the middle of a project because the antenna position is very important. Also, the PCB layout is very important. So this can be done by CST and should be handled at the very beginning of a project. So this optimizes the design project, and also we can consider all the mechanics. So this is really helpful, and this is the tool we use. All this workflow is the workflow that we use to design this product, for this antenna product, for our colleagues in Nordic Semiconductor. Let's see in this video, again, this is the platform with all the components, and here we have the layout for allocating the trio MX10. And again, it's very easy. We have the enclave model for the trio MX10, and we import that enclave model to our CST file. You have the battery, USB connection, and other kind of connectors. The losses in the dielectric of the PCB also take into account. The plastic cover is also have some losses, so it's also taken into account. This is the trio MX10 encrypt product with all the pads in orange color. And again, this is easily imported, as you can see on the screen, easily imported in your CST file. And well, in case you have a MIMO device or you want to add other antenna boosters, you can do it. You can import as many antenna boosters in an IoT device as you want. Okay, 1, 2, 3, whatever. Okay. And after some rotations, I'm going to move this forward. After some rotations, you see that the antenna booster is integrated in the device, and step number 1 is done. So the antenna position, the PCB layout has been optimized, and this is ready for simulation, and even taking into account the plastic core. In this case, since the platform was really small, it was 50 by 50, so it's really a challenge because we need to operate at several LT1s. In this case, from 700, which is very low frequency, up to 960, plus 1710 up to 2200, plus GPS. So in this case, with a passive matching network, it's difficult to manage this huge multi-band bandwidth. So in order to achieve all this bandwidth, what we propose is a tunable architecture that is based on this scheme. We have the front-end module, the transceiver from Nordic Semiconductor, with 2 IOs. One input-output port is for transmitting and receiving LTE. The other input is for receiving the GPS signal. And these transceivers have some control lines that controls the switches that are by Corvo, but are many other available. So the transceiver has all the intelligence in controlling the switches. So for instance, if we need to operate at 798 up to 748, the transceiver put these switches in this state. So now we can design a particular matching network. So we only match at this frequency range, which is much easier. With only 1 or 2 components, we can handle this bandwidth. In the end, this is the wave that goes to space, or also the wave that it's incoming and it's received by the transmitter. For another state is the same. So the transceiver is changing the states of the switches and so on. And for GPS, the same. We receive the weak signal from the satellite. The signal is matched with the GPS matching network. It's magnified by a low noise amplifier and eventually reaches the GPS transceiver. The question is, can we handle all this sophisticated system with CST? Yes, for sure. We can put here our RF generator, our ports, 50 ports, and we can handle these switches as shown in this picture. This is the switch. It's a very tiny component. It's only by 2 by 2 millimeters, so it's really a small component like an inductance or capacitor. And the S parameter are available that take into account the isolation as well as the insertion loss of all ports. So this block here are the full parameters. It's a 9 by 9 matrix. Also the matching network, some patch, the delay of the patch effect can be taken into account, the antenna by CST, and at the end the feeding port that will be the 50 feeding port. So all this chain can be easily modeled, so the estimation of S11 as well as efficiency are much more accurate if you take into account in your design all the components, not only the matching network, but also the RF switches. Here we have an illustration of how this works. In blue, we have one matching network that is for operating in the lowest frequency range, around 700. When the transceiver needs to operate at another frequency range, it changes the switches. So you see here that now the matching network changed to the pin, which will be another matching network with only 2 components here. So we change another state. Also, we can operate in the higher bands with this state, and so on. In a third state, with the brown color and with the red color, we are covering more frequency bands up to 960. And finally, the GPS that will appear here in black color, which is this matching. So with this structure, you see that although the platform is really small and it's a challenge to design antennas and even antenna boosters at such a low frequency region of 700, with this structure, we were able to handle all these frequency bands, and this is the real structure that is operating in the Thingy 91 by Nordic Semiconductor. And here, what we have is the comparison between simulation and measure efficiency, and again, in the lowest frequency region and in the highest frequency region, GPS, as well as all the high frequency region. You can see that the agreement is pretty good. In this case, we have less than 0.2, 0.3 dBs of error, a little bit more in the high frequency, but nevertheless, it's a fully populated PCB, fully of component, plastic cover, and the prediction is very good. So it allows us from the very beginning to know that we can handle this project and successfully bring to production. And this is what happened. So the simulation is really useful, because if the simulation tells you in advance that you are going to have problems for certification and so on, you can say at the very beginning that, well, there's a problem with this platform. We should do something. So this is very convenient always to do simulation, and always because this optimizes the PCB, the antenna location at the very beginning of a project. So the antenna is very important, and it should be taken into account always at the very beginning. And with simulation, it's something that we can handle very easy with CST. This is some examples of the variation patterns. For these small platforms, the variation patterns at the low frequency bands are quite omnidirectional, with a directivity of around 2 dB. As you increase in frequency, they increase a little bit in directivity, but nevertheless, the directivity is moderate. It's around less than 5 dB. It's usually quite omnidirectional patterns, so at the end you can receive signal from every location. That is good to know variation patterns, because you can always see, well, here I receive more signal from this direction to the other direction. Perhaps I need to put upside down the device if I know that the signals are coming from a particular direction. Okay, but if not, usually for these devices, this kind of IoT devices, variation patterns are most omnidirectional, which is good. And just to conclude, let me show this last example. This is also a new real example you can see on the screen. By the way, let's put this picture. You can see that what we simulate from the customer is the same that the customer is bringing to production. And here we have many connectors, the front-end module, more connectors, components here, the chips. So everything is taken into account in this fully populated PCB for GPRS, and some bands of GNSs, GLONASS, Beidou, and GPS. This is from NuvaThings, a company that designs IoT devices for everything related with security systems, human automotion, gas fire detectors, water leakage, smart farming, sensors, and so on. So this is a nice example of how simulation helps a lot in step number 1. Optimize the platform and choose the antenna booster and put the antenna booster in its location. Step number 2, design the matching network with CST. We obtain this parameter and then we design the matching network. We can get help from the obtaining lab software, and if not, we can design our matching network. And step number 3 is bring that matching network into real product and measure the H11 in efficiency and without human intervention that works and we can bring to production. And here are some results of efficiency at the GPRS bands, in the low bands and high bands. You can see that the average is pretty good, about 59 and 62. And in here we see that we have 2 ports. One port is for GPRS and the other port is for the GNS. We have a transceiver that has 2 input-output ports. So in this case, we are using this trio antenna with 2 ports. And in some products, we are already doing that with 3 ports. So one port can be handled for LTE, another port can be handled the GNS frequencies, and another port can handle Bluetooth frequency bands. So it's really a quite flexible antenna technology, not only for multiband, because in this port here, it's multiband, but it's also multi-communication because you have LTE plus other communication systems, GPS, and eventually we can put another port for operating and Bluetooth. This is the workflow that the sound system has to support antenna design, and it's good because it's the same workflow that we are using at Cactus Antennas, from receiving the requirements from the customer, to use the encrypted models for the customer and work with the customer to optimize the PCB, the antenna location, if there is 1, if there is 2, there is 3. So we need to handle with the couplings with antennas, the coupling with other components. Then we assemble everything, we integrate the antenna in the device, we obtain these parameters, the efficiency, radiation patterns, and even we can handle with CST the human body. So if we have an antenna in a cow, for instance, for farming, we can take the full cow, or if in a body, in a smartwatch, we can handle the wrist or in the head. So everything can handle with the CST. And related with this flow, with this workflow of the soul, we have to say that at the very beginning stage of a project, we have this wireless fast track service that will help you in case you want to use this technology and at the very beginning you need help and you want to be familiar. You can use this service that we can help in integrating the virtual antenna in your IoT device. And this is, everything is done by CST. All the IoT device, your IoT device with all the mechanics fully populated, it's handled with CST. And these steps, step number 1, so we help in optimizing the PCB layout and choosing the best antenna booster. Step number 2, we can design the matching network. And step number 3, then we go to prototyping on the real product. This can be done. And obviously, once you are familiar, the design of virtual antenna in IoT devices, it's very easy and fast. So you can do it by your own. So the final question is, well, where we can find these encrypted models? It's very easy. You go to fractusantennas.com webpage. Once you are in, you go to the tab products, and you will see the virtual antenna products. For instance, you choose the RAM extend here because you are interested in using this antenna booster. You click in here, and there is a tab at the right part at the bottom that says Design Information Pack. Click there, and a zip file opens. And in that zip file, you have plenty of information. One is CST Studio Suite encrypt files. If you open that, you will find your CST ready to use in your CST designed for IoT. And you also have some PDF with some user manual, which is at the end some basic information, only 3 pages information on how you can feed this antenna, the information, and some more help that you can find in this. So at the end, the purpose is that with this virtual antenna and the CST and this systematic way, you can now use this component as you use any other component. For instance, as you use amplifier or you use filters, you can design your own IoT device with antennas by your own. So you can take the antenna booster, the grid model, you can design your matching network, and you can do it single band or multi-band by your own using this systematic way of design. Here is an example of the user manual. And just to conclude, in summary, with virtual antenna, we see that we have very small multi-band and multi-communication antenna booster. They are off the shelf, so ready to use, and they are pick and place. So this is very good for production. And the virtual antenna products, encrypt products with CST, enable us to optimize from the very beginning all the design flow chart and also optimize the design and go to production. So from simulation to production in a flash, as you can see in this nice plot here. So I would like also to thank you, all the people following from home. Thank you for watching. Thank you to our friend, Dr. Joao Costa, and also Vanessa Clement for all your kindness and for your support. All the Sound System team for organizing this webinar and supporting these hard days of coronavirus. Thank you for organizing so we can communicate each other and share knowledge. Also to the European Association of Antennas and Propagation for helping to promote this event, and in particular to the working group of software and modeling. In case you are in Shanghai, in China or in India, also we have some headquarters there in case you want to contact our facilities there. And if you want to get more information, more technical rig and more technical physical insights, because you are more curious about the technology, okay, you have here a reference that we can share with you at the end, okay, with papers in IEEE as well as other magazines. So on behalf of Practus Antennas team, and we would like to thank everybody. Thank you all for watching and the Sound System for organizing this. Thank you very much.